once. We got a question here. Afternoon, everybody. Yes, afternoon. Okay. Well, if not, I'm going to proceed with chapter 4, and we're going to get back into chemistry. We're going to get back into the model of how we think at the current time how the atoms are put together. Now, I've been asked this numerous times: is this really how accurate is this model? This is a model based on the data we have to date. This is the best explanation as to what we think is happening with respect to the atoms and how they're put together. Tomorrow, who knows? We might get a whole new ball game. But as it stands, with science, things always change constantly with new data coming in, new things coming in. So as it stands, this is our particular model. Okay. So let's start with chapter 4 and move on to chapter 4 here. All right. So way back in 1800s, and this is interesting that during the 1800s, we start building our model of what we thought what the atoms consisted of. Okay. Now, Dalton proposed that an element is made up of tiny, indestructible particles that he called atoms. Now, the idea of the atom is not new. It went back to the days of the Greeks. They had an idea about atoms. That's where the term comes from. But anyway, Dalton says, okay, these are tiny particles, indestructible. Not 100% correct, as we learn later on, that these tiny particles themselves are made up of even smaller particles. Okay. And those particles are even made up of even smaller particles, but we're not going to talk about those. That's for an advanced physics class, chemical physics class. But we're going to be talking about the particles that atoms are made up. We're just 3 particles: the proton, the neutron, and the electron. And keep it in mind, those little guys are even made up of smaller particles, but we're not going to talk about it. Anyway, he also proposed that all atoms of an element are identical and have the same properties. Okay. Well, not 100% true. Okay. Because we find, as far as properties are concerned, yes, they're all identical, but they could be different properties. For example, we kind of briefly touch on the diamond. The diamond is made up of carbon, and so is graphite, which has carbon in it. Same element, identical element with the same number of protons, electrons, and so forth, but totally different properties, right? We got the diamond, which is the hardest thing on Earth, and we got graphite, which is a dry lubricant. Yet they're made up of carbon, and that's because the way their atoms are put together relative to themselves, which affects the properties. Okay. Now, he also proposed that atoms of different elements combined to form compounds, and this is what we still have to this day is our definition of a compound. Those are compounds are made up of 2 or more different atoms. For example, we have 2 diatomic elements here. We know they're diatomic because they're the same color, same shape. The 2 diatomic gold color, maybe yellow, mustard color, and the 2 red. They combine by some chemical process to form 2 products, of which now the new partners are a red one and a gold one. So they have created a compound from the elements. Okay. Now, the other aspect about his theory was that when they come together, like so, they come together in whole numbers. 1 to 1, 2 to 1, 3 to 2, any combination of these whole numbers, but whole numbers. Okay, not partial, not quarter, not half an atom or 3/4 an atom, but they come together in whole numbers. Hence, we have, for example, the formula for H2O, which is a compound, right? Because we have 2 different elements, hydrogen and oxygen, and they come together with 2 hydrogens and 1 oxygen. In the previous chapter, we had one example of physical properties where we had H2O2. If you remember that one, that was hydrogen peroxide. A simple thing by adding another oxygen in that combination, you made a whole new compound. Okay, so they come together in whole number ratios, make the compounds. Now they can combine together either, like I said, in different numbers as far as ratios. For example, C, capital C, capital O. That is the formula for carbon monoxide. Monoxide meaning that one oxygen, as compared to what we're familiar with quite a bit, all of us, is carbon dioxide. Di, the prefix for two. Notice there's a subscript 2. Okay. Now, you will always be told the way the compounds are put together, and I mentioned this before, is there is a central atom when there are more than 2 or more elements attached to a compound. There is a central atom. So in carbon monoxide, there really isn't a central atom. There's only two atoms coming together. Okay. But in carbon dioxide, notice the red color center. That represents carbon, and that is the central atom, and the other 2 oxygens are bonded to the central atom. You'll be told who the central atom is. Sometimes it's quite obvious because 99% of the time when we write a formula, the central atom is normally written as the first element, as the case here with carbon dioxide. Okay, so you can make a reasonable deduction that when you see a formula, that first element is the central atom. The only exception here is water, H2O. By convention, people write it down H2 and then O. Oxygen is the central atom in water, and the hydrogens are written first. Technically, if we go by convention, it would be OH2, O being the central atom. But people have been writing it as H2O for so long, you just keep it that way. Okay, so, and when they combine it, because the atoms of 2 more elements, when they combine, they can form totally different compounds. Okay, carbon monoxide has totally different properties than carbon dioxide. Plants need carbon dioxide. Nobody needs carbon monoxide. It's a poisonous gas. Yeah. Now, keep in mind the year. We're looking at the beginning of the 1900s. Okay, so about 1897, there's a scientist by the name of, I call him JJ, good old JJ Thomson. He is given credit for discovery of the electron way back in 1897. And what he did, he created a piece of equipment, what we call a cathode ray, which really, if you have your grandparents, or maybe your parents have an old-fashioned TV, those big old heavy TVs, elongated, that TV was created in the same, because of this work of J.J. Thomson, we have the original television. Okay, so I thank J.J. Thomson because he gave me cartoons as a kid. All right, his work. Anyway, what it does is he has what's called a cathode ray tube. Okay, and what it does, it creates a particle, and by using the electrical fields and magnetic fields, he's able to move that particle, and let it hit and now we're going to go through a video of it. Let it hit a screen. Now on the screen, you're going to see here, when that particle hits the screen, remember that particle has energy and has high energy. And when it hits the screen, it transfers that energy to the material on the screen. So the material on the screen now absorbs that energy, and it kicks it up to the next higher energy level. Keep it in mind about what I said about nature. Nature doesn't like to stay up in a high excited state. It drops back down. So that material on the screen drops back down to its stable state, but it has to release that energy that it picked up, conservation of energy, and it releases it as light. And so what we're going to see is this beam hit the screen, and then we're going to see a beam, a light material fluorescence on the other side of the screen. Okay, That's what happens essentially with respect to even the screen you're looking at now. You're looking at the material that is the atoms are getting excited, they emit light to get back to the ground state, and you end up with an image. So anyway, let's see. Hopefully you can hear what the commentator is saying. So there'll be the next slide here. Come on. Okay. So notice here, a particle is created and is being ejected out with through magnets. We're going to not get into details of it, but that red particle now hits that screen up front and transfers this energy to the fluorescence material on the screen. Okay. And you end up seeing the light. And so what's happening here is like the old-fashioned televisions, because that's why those guys were so heavy, because in the back of the TV, there's 4 giant magnets that allowed to direct that beam that's being created. So we have an electrical current running through here, and guess what? That beam was deflected. Keep in mind that every time when you, oh, let me let somebody in. When you have an electrical current going through point A to point B, along with it has a magnetic component. Okay, so that electrical current has with it a magnetic component. And that means that that beam must have a charge, because if that beam was neutral, this current wouldn't have any type of an effect. Okay. And so anytime, like I mentioned, every time there's a magnetic charge movement, it has with it a component which is a magnetic component. That's why we have electric motors, okay, and generators, because electricity can have with it magnetic component. In fact, I'll show you that here in a second. So here we got a magnet, okay, and the south end is deflecting that beam. Again, further stating that that beam is a charged particle. Okay, don't get freaked out with this equation. We're not concerned about this equation. What he did was able to calculate that ratio, E over M. Okay, M is the mass of the electron. Down the road, somebody else calculated the E, and once he knew what that E is, guess what? You can calculate the mass once you know the ratio. Okay, and once you know one of the variables, and we find out that mass of that electron is extremely tiny. This is an example of how we can find masses of particles that are so tiny we can't weigh them, obviously. So we're doing measurements of mass indirectly, okay? But nevertheless, and so you calculate that ratio, and when somebody else down the road calculated E, guess what? We got mass. All right. Okay. And so from his work, JJ proposed his model. Okay. Now, prior to this, we know we had the model of the atoms, but we didn't really have an idea how things were put together or that there were particles in there. And so we started to build up a model. But what he proposed was this. JJ proposed that in the center of the atom is some kind of a positive entity. And these electrons are somewhere around it. Okay. And so his model is classified as the plum pudding model, where the electrons just are arbitrarily just sitting there, somewhere in the atom. Well, that held on for a little bit. Notice the time, 1904. And keep in mind, there's other scientists during this time period. This is the time of Einstein. This is the time of numerous, J.J. Thomson. There was numerous scientists in this time period. They were just as bright, if you will, as Einstein. But I think Einstein had a better public relations person, so he's more noted than the rest of the scientists. A plethora of information, knowledge occurred in this time period, 1900s all the way into the 20s and 30s. All right, so we got 1904, that's his model, plum pudding. 7 years later, another scientist comes along, Ernest Rutherford, a British scientist, and he is credited with discovering the nucleus, okay? And or nucleus / proton. Now, what he did, he also used particles, and he created these particles, and he kind of shot them into a foil of gold. Okay. Now, the proposal here was this: if the plum pudding model was the model that we had, this correct, then all these particles would just go right through the gold, and that was it. But what he found was that some of these particles were ricocheting in angles. And it's like, oh, something's happening here. Okay. And so he said there must be something in the nucleus that's pretty dense to cause these particles to ricochet. It's analogous to shooting pool. You got the cue ball, you're shooting a ball and you want to shoot it to an angle. You hit it just right, and that ball goes to the angle. So he was really surprised. So similar type of setup. The fluorescence is set up where you can analyze this, but he was watching this fluorescence coming at different angles. So we'll go through that video. Okay. Notice here, again, he created what are called alpha particles. We're not too concerned about these particles, but they're being generated. They go through a gold foil. A lot of them, majority of them, are hitting the front of the fluorescent material, which is circular here. But instead of all of them hitting there, occasionally you would get fluorescence at an angle, right there. Okay, and so he proposed, Rutherford, that in the center must be a very dense chunk of matter. And he proposed that is the nucleus, and the electrons are kind of situated still, not knowing at this point how, around the nucleus. So the beginning of the model, like analogous to our solar system, begin to be formed. Okay. Now that's 1917. Rutherford, he's discovered the nucleus slash proton. Okay, and then we had J.J. Thomson again, 1904 earlier, who was credited with discovering the electron. And it wasn't until 1932, in the 30s, that Chadwick was discovered the neutron. So we have the three particles that we're going to talk about: is the electron, and in the nucleus, the proton and the neutron. Okay, essentially, what was found that the atom is essentially a lot of empty space. Okay, and the electrons are moving around the nucleus. But at this point in time, not quite sure how. We know they're there, but somehow we don't have a model for how the electrons are situated. Okay, so each atom has a very small, dense nucleus, and with the protons and the neutrons. Now, the thing to put in long-term memory: elements can lose electrons all day long, lose or gain electrons all day long, lose and gain neutrons all day long. I'm being exaggerated here, and it's still that element. Okay. The proton, the moment you lose or gain a proton, you become a different element. So it is the proton that determines what type of element you are working with. Okay. That is what defines an element, because the only difference between a hydrogen atom and a helium atom is a proton. Helium has one proton. Excuse me, hydrogen has one proton. Helium has two protons. And it goes on like that until you get to a number 118. All right, so to give you some perspective, if the nucleus was the size of, say, a small marble, and then the atom itself, the size of the atom where the electrons is, it would be the size about as big as a Cardinal Stadium. Okay. So put everything in perspective, how much empty space we have there. There's some numbers there to tell you, again, roughly the diameters of the atom, 10 to the negative centimeter diameter. Pretty small, pretty small. Another analogy to help you out is if I were a hydrogen atom and I represent the nucleus, my electron will be about 3/4 of a mile away. And yet, even as far away as it is, there's a force that keeps that electron on my nucleus. There are forces out there. We don't quite understand what's happening, how it works, but we do recognize there's a force that holds that nucleus, because it holds it back. Because remember, the electron is negative, the proton is positive, and so why don't they just come into each other and collide? Because they should attract each other, but something's keeping that distance apart. Okay, and that electron, we're going to learn, is on orbit. It's not crashing into the nucleus, but it's staying back where it should be with respect to its radius. All right, so we have the three particles, subatomic particles. We got the electron, the proton, the neutron. Each had their symbol given in the second column here: E, P, and N. Superscript negative for the charge. Okay. Its location is outside the nucleus for the electron, and it has a charge. Now, because these things are so small, we have given them what are called relative mass or atomic mass units. Okay, because these masses are so tiny. So what does that mean, relative mass? Well, let's say I'm 200 pounds. I'm 200 pounds. There's another individual at 400 pounds. Okay. Now that means his relative mass is twice mine. So I'm 1. The other individual would be a relative mass of 2. Okay. Because the numbers, the masses are so tiny that we just give them a relative mass. So proton and neutrons have a relative mass of 1 atomic mass unit. The electrons are so tiny that essentially we give them a relative mass of 0. We say they're massless, but that is not true. The mass is so tiny. that it's a relative mass of 2. And for example, if you were to weigh 1 pound, if you were to weigh like 1,800 pounds, 1,836 pounds, the electron would be 1 pound. That's the relative mass. So we tell it 0. Okay. And, and the electrons, to keep in mind, these are the same electrons that give you that bad hair day that make your hair go poof. And, it's the same type of electrons, atomic particles, that as you're walking on carpet and you touch something, you get zapped. Yeah. Or the ones, those are electrons. They have a big, big part in chemistry. Now, atomic notation. Basically, this is the way we write the, the elements. Okay. SY represents its symbol. Whatever the symbol, there's 118 symbols for each element. Now, A, superscript left, I repeat, superscript left in the A position is what we call the mass number, okay? And subscript Z is what is called the atomic number, okay? Atomic number. Now, the atomic number represents the number of protons and electrons. Now, what do you call it? Let me pull it up. On the periodic table that we supply. Here's the elements. The number on top of the symbol is the atomic number. That represents the number of protons and the number of electrons. Okay, so hydrogen, number 1, has 1 proton, 1 electron. Potassium, okay, potassium, atomic number 19, has 1 proton, 19 protons, 19 electrons. Now, let me ask you a mathematical question. The protons have a positive charge. The electrons have a negative charge. Okay. If I have 19 positives, 19 negatives, what is my net charge?
Neutral.
0, exactly. All right. So every element up there has a net charge of 0 because they have equal positives and equal negatives. When we get down the road, we're going to find out that these elements are either going to lose electrons or gain electrons. The nonmetals, as I stated earlier before, I said lose electrons. And when you lose electrons, you have now a new net charge of whatever that number is. For example, sodium starts off with 11 protons and 11 electrons. Okay? Because it is in group 1A, and this will come clearer here in a second, it will lose 1 electron only. So now it has 10 electrons. So if I got 11 positives and 10 negatives, guess what my net charge is now? Positive. And that is what you put on your French fries, that sodium. That is what we ingest, the ion, the electrolyte, which you're more familiar with that term. And those ions are nothing more than the elements that have gained or lost electrons. We will be able to predict how many electrons they lose and gain based on what group they're in. That group is at 1A number. So everybody in group 1A, everybody from hydrogen down to number 87, they have 1 electron in the outermost layer. That's why they're in that group. Okay, but more on that later on. So that's why I emphasize that I reference the periodic table quite a bit. You get a lot of information on the periodic table. And so the atomic number represents the number of protons and the number of electrons. So you can, at all the 118 elements there, be able to determine how many protons it has and how many electrons it has. So if someone says, okay, element number 25, how many protons? 25. How many electrons? 25. What's his net charge? 0. Okay. All right. Now, with respect to mass number is a whole number. I repeat, mass number is a whole number, not to be confused with the atomic weight. The atomic weight is a decimal number. Okay, back to the periodic table. The number underneath the symbol, for example, sodium, is 22.99. That is the atomic weight. That is not the mass number. Okay. And I'm going to show you how to get to that mass number very quickly, and I'll explain here in a bit why. What you do is you take the atomic weight and you round it up to the nearest whole number. So for 22.99, what is the nearest whole number when you round that number up?
23.
23. If I take that 23 and subtract 11, guess what I have? 23 minus 11, which is the atomic number. Okay. What's 23 minus 11?
12.
12. Exactly. 12 represents the number of neutrons.
Yes.
Okay. Because the number of protons and the number of neutrons in relative AMUs is the mass number. Now, why is the atomic weight a digital number? We're going to learn that all these elements, some of them have extra particles. Some you all heard of carbon 14, carbon 13, maybe a carbon 14 where you do dating of old stuff. Okay, well, there's something called, for example, carbon 11, carbon 12, carbon 13, carbon 14. Everybody's carbon. Okay, they've not changed. Okay, carbon 11, carbon 12, carbon 13, carbon 14, all have 6 protons. They're carbon. The only difference between those guys is they have either an extra neutron or one less neutron. Now, what happens is out in nature, there's a percentage of carbon 11, percentage of carbon 12, a percentage of 13, and carbon 14. Okay. And just like your grade is, we say there's a certain percentage for the homework, certain percentage for the activities, percentage for the exams. Okay. The atomic weight consists of the average of those whole numbers and their percentage that they have out in nature. And so that is why I can take the atomic weight and round it up to the nearest whole number. And that gives me the mass number, because that atomic number, atomic weight, is closer to the most abundant isotope. So carbon 12 is the most abundant isotope. There is carbon 11, carbon and 13, and carbon 14, but they represent a smaller percentage. There's more 12. So when I average those 4 numbers, 11, 12, 13, and 14, and then I count the percentage that they have, I end up with the number of 12.01. Okay. The point of all this is that the atomic weights are not used for significant figures. Why? Because the atomic weights are the average of the isotopes, which are whole numbers. Like I said, average 11, 12, 13, and 14. If I average those numbers up by themselves, and then I have to account for the percentage, I end up with 12.01. So when you take the average of whole numbers, you have an infinite number of significant figures, infinite number. So you can, just by looking at the periodic table, state, okay, who is the most abundant isotope for nitrogen? I go next to nitrogen. I take that 1401, I round it up to the wholest number, nitrogen 14, okay? And there's nitrogen 15, but it's not as abundant. Otherwise, my number would be closer to 15, but it's closer to 14. All right, so let me go back to where it was. So the mass number, again, is a whole number, and that is the sum of the proton and the sum of the neutrons, which are whole numbers in themselves, okay? The atomic weight here is not even mentioned anyplace. Everything here, atomic number, number of protons, number of electrons, those guys are whole numbers. The mass number and the number of neutrons, everything here is a whole number, okay? Let me get here for a second. I know what I'll do. Bear with me for a second. Let me pull up something here, and it will hopefully make a little more sense. Now, to see this, if you go to your modules, and let me share here. If you go to your modules on the Canvas course, you have a module called Additional Resources, okay? Now, if you click on Build an Atom, you have a simulation you have a simulation, and click on Atom, okay? And here you have the subatomic particles we've been talking about: protons, neutrons, and electrons. Now, as I mentioned, notice something here. I can see the charge and my mass number. When I grab a proton and I come near the dotted line and just release it, guess where it goes? Oh, back to the container. Go a little bit closer. Goes to the center. You see that? Guess what it made? Look at the symbol. It became hydrogen. Now, what's my net charge at this point? It's a +1 because I've only added a +1. And so if I add an electron, because we know that a hydrogen has one proton, one electron, and I have a net charge of 0, as we talked about. And it has a mass number of 1, okay? Because there's only one proton. Now, the neutrons are neutral. Now, if I add a neutron, it goes right to the center because that's where it exists. Guess what's happened? My mass number now goes to 2 because the mass number of a neutron equals to 1. I have made an isotope of hydrogen. Okay. If I go one more, I made hydrogen 3. I still have hydrogen. You see, the neutron, by adding neutrons, I create what are called isotopes, and that increases my mass number because that mass number, that neutron weighs 1. Eventually, what the neutrons do is to help stabilize that hydrogen. So there are 3 isotopes of hydrogen. There's hydrogen 0, really, because this is the original hydrogen, has no neutrons, okay? Has one proton, one electron. And then there's hydrogen 2, and then there is hydrogen 3. Those are the isotopes. Now, if I go in and I keep adding protons, notice I create new atoms, right? Boron. And we'll come back here for a second here. I want to get to carbon. Okay, here's carbon. Carbon has 6 protons. Our charge is +5 because it's got 1 electron here. I got to add some more electrons, so I have a net charge of 0. Notice something. If I grab an electron and come to the center, it goes to the outside dotted line. We're going to talk about this. We're going to learn that these electrons are not just haphazardly put in there, but they're in specific energy levels. Our charge is now a net charge of +3, but we're going to add 1 more. Okay. And so now we have 6 carbons, and we're going to add this. Oh. Let me make sure I get to carbon 12. Okay, the most common isotope is carbon-12. Okay, it has six protons, 6 neutrons, 6 electrons, a net zero charge. I mentioned earlier, there is an isotope called carbon-11, and the difference is it's minus 1 neutron. Okay, there's carbon-11 right there. If I add a neutron, I'm back to the most common isotope, carbon-12, but there's also carbon-13. And guess what? Carbon-14. Okay, notice here you got the number of protons, the number of neutrons, the number of electrons. And like I said, we can add or gain neutrons and electrons all day. As long as we don't change the protons, we still have that element. Right? Anyway, these are isotopes, and all the elements have a specific number of isotopes, not just that element itself. Otherwise, their atomic weight would be pretty much even number. So take a look at that simulation that will assist you grasp how the atoms are put together. So every atom of an element has the same number of protons, and also has that equals the number of electrons. So you can pick any element up there, any neutral element, okay? And just by knowing its atomic number, you know the number of protons and the number of electrons. Okay, and like I stated, the number of protons defines an element. Carbon will always have 6 protons. Okay, but it can vary with respect to neutrons, like I just demonstrated in that simulation. And that's true for all the elements. Some elements have 2 isotopes, some have a numerous number of isotopes. And that is why that atomic weight, again, it has a decimal number, because those are averages of whole numbers, which are the isotopes of all the elements. So you think about it, even if you did a simple average of 11, 12, 13, 14, average that out, see what number you get. You're gonna get a decimal number. Okay, so atomic mass units, protons and neutrons always have an atomic mass unit of 1. Their relative atomic weight, remember, because they're so tiny. So they've been defined as to give them an atomic mass unit of 1 for the proton and neutron. And for the electron, because it's so tiny, is basically 0. So the mass number is the summation of the protons and the neutrons. And I already explained how you can determine the mass number very quickly for the most abundant isotope. And that is by taking the atomic weight and rounding it up to the nearest whole number. Okay. So let's do a couple here more. Let me call it. And so for, let's say, can anybody tell me for oxygen? Oh, let's do fluorine F. All right, fluorine. How many protons does fluorine, the element fluorine, have?
9.
9.
9.
Exactly, 9. How many electrons?
9.
9. How many neutrons?
10.
Exactly, 10. Because it has an atomic weight of 19.00. It's already rounded to the nearest whole number. Subtract the 9, so that difference is the number of neutrons. Okay, if let's do its neighbor, neon. Neon has 10 protons, 10 electrons. How many neutrons does neon have?
10.
Exactly 10. And we're talking about the most abundant isotope, because we're going to round it 20.18 to 20. Okay. Now, how do we write the other isotopes? Well, we'll go back to the slide. Okay. Okay, so this is an explanation for the most abundant isotope. We just go get the atomic weight, round it up to the nearest whole number, and just subtract this, the number, the mass, not the mass number, atomic number. Okay, but sometimes you may have a problem that says, okay, write the atomic notation for potassium 40. And you're like, whoa, wait a minute, what the heck is that? All right, well, go back to the periodic table. Look for potassium. Potassium is K. Okay. And it is right there, number 19. Okay. Now, just by looking at it on the periodic table, what is the most abundant isotope for potassium? That would be potassium 39, right? Because all you got to do is take that 39.10, round it up, and you got potassium 39. That is the most abundant isotope. But the problems ask about potassium 40. So what do you think the difference is between potassium 39 and potassium 40? Is there any difference? Yeah. Potassium 40 has one more neutron. That's why it's potassium 40. Because the most abundant is potassium 39. Okay. 39. And so the way we write these isotopes is we write the name out, potassium hyphen, and then whatever atomic number we need. Okay, so let me go back to this. If this were the most common isotope, potassium 39. Okay. Potassium 39, that would be the mass number for potassium. Now, they both have the same number of protons. Okay. Same number of protons because they're both potassium. And so they have 19 protons. But the mass number is given to you. So we have to write the notation potassium 40 with the 40 in superscript left. We don't have to calculate anything. It's just given to you. If we were going to do potassium 39, we would replace that 40 with 39, which happens to be the most abundant isotope for potassium. Okay? The atomic number is subscript left. Okay. Now you'd be tempted, put it on the left side. That is the notation that is utilized, the atomic notation format. Okay? With mass number upper left, atomic number lower left, the symbol to the right there. Okay. In this scenario, they ask you, how many neutrons are there? Well, you simply subtract the 2. You got 21 neutrons. Well, how many neutrons would be in potassium 39? Anybody know?
20.
Pardon me? 20? Exactly, 20. See, it's still potassium. Potassium 39, potassium 40. It's still potassium because they both carry 19 protons. The difference is potassium 40 has extra luggage. It has one more neutron. Therefore, its atomic mass unit goes up by 1 unit, 40. Now, they do have totally different properties. And the reason they have different properties is because they get the extra neutron in there. They're still potassium. Okay. All right. Question here says bromine 81. All right. Well, let me ask you a question before we figure this out. Is bromine 81 the most abundant isotope? Okay. Well, to answer that, you got to go to the periodic table. Remember, I said I make reference to the periodic table quite a bit. All right. We search bromine. Bromine is number 35. Okay. And you figure out the most abundant isotope, guess what? We round up that 79.90. And what is that? 80, right? So bromine 80 is the most abundant isotope. That means that bromine 81 is not the most abundant isotope. It's an isotope. There's bromine 81. And there's got one more neutron than bromine 80. And so we write the atomic notation. So 81 is given to you there. You don't have to do anything. Now, sometimes they give you the full name bromine. Occasionally, you may find it done in this manner where they give you the symbol and then the hyphen and then 81. Okay. Or BR-80. Okay. So sometimes they write it out. Occasionally, you may see the symbol hyphen and then the number. Okay. And that's the and I ask you to write the atomic notation for that particular element. And so that number after the hyphen is given to you. You have to look up, if you don't know what the atomic number is for bromine, you can use a periodic table and determine its number 35. Okay, which it is. I'll go back and show you. Bromine 35. See the 35 sitting on top of the symbol? All right. Okay, and to determine how many neutrons are for bromine 81, you simply subtract 81 from 35. That's it.
46.
46, that is correct. Okay, and for bromine 80, which is the most abundant, you would be 40, right? 45 neutrons. Okay. All right. So this is what I talked about earlier about isotopes. All the elements have isotopes. Some have, like I stated, 2 or 3. Some have more. But the only difference between isotopes is the number of neutrons. Okay, they're still that element. They just differ in the number of neutrons. And so here we have carbon 12, 13, and 14. There is also carbon 11. Okay, and guess what? There are 6 protons in all of them, okay? Because we haven't changed the number of protons, but we do change the number of neutrons. So carbon 12 has 6, carbon 13 has 7 neutrons, carbon 14 has 8 neutrons, all right? So you can see here, if you were to average these in numbers out, carbon 11, 12, 13, or 14, how you can end up with an average of something 12 something without the percentage of each, and that's why you get the atomic weight as a decimal number, because that is the average. The atomic weight is the average of all the isotopes and the percentage that they have in nature. Okay, here you have a table that asks you to fill it in. You got carbon, excuse me, I got carbon in the brain now. Oxygen 16, oxygen 17, oxygen 18, okay? So the mass number is given to you by that number after the hyphen. So here we go, mass number 16, 17, 18. They're all oxygen, so they all have the same number of protons, and guess what? The same number of electrons. The only differ is in the number of neutrons, okay? Number of neutrons. Now, if you look at just look at here, 8 plus 10, what is that? 18, right? 8 plus 9, isn't that 17? And 8 plus 8, isn't that 16? Okay. And so that mass number is the sum of the number of protons, and the number of neutrons. Okay. All right. Here. And this is again why that atomic weight is a decimal number. For example, carbon 11 is a trace amount. Carbon 12 represents about 90, almost 99%, 98.89%. Carbon 13 represents 1.1%. And again, those carbon 14 is a very small minor amount. So you can see that carbon 12 represents the most common isotope of carbon, and that's why when we average these numbers up and put in the percentage of each contribution, that number is closer to 12. And hence, if you look at the periodic table, the average of these numbers gives us the atomic weight, which is 12.01. And that is why you can take the atomic weight from the periodic table, round it up to the nearest whole number, and determine which is the most common isotope. Okay? All right. So here, the question is, all right, we got lithium-6 and lithium-7. The question is, who is the most abundant isotope? Well, to answer that, guess what? We go back to the periodic table. We look for lithium. Lithium is number 3, okay, Li, and we look at its atomic weight, which is 6.90, rounded up to the nearest whole number, which gives us 7, which tells us that lithium-7 is the most common isotope. Okay. Chlorine-35, chlorine-37, which is that? Well, we go back to this trusty periodic table. We look for chlorine, which is number 17. Its atomic weight is 35.45. Rounded up to the nearest whole number, that becomes chlorine-35. Chlorine-35 is the most abundant isotope. So without having to memorize all that, you just simply go up to the periodic table, find it, round the atomic weight up, and you got your answer. Okay. Now, in the periodic table, you'll see a lot of numbers in parentheses. Those they give you they're in parentheses, but in whole numbers, and they're very unstable, extremely radioactive, and so we don't really have a good atomic weight for them because they're so unstable. So you'll see them written in parentheses, like curium number 96, named after guess who? Madame Curie. Okay. Anybody know by chance where Madame Curie was originally from? An amazing lady. She had 2 Nobel Prizes. 2 Nobel Prizes, and her kids, exactly, she was from Poland. A lot of people say France, but no, she went to France to get her education because she could not get her education in Poland because women were not allowed to go to school and higher education. So she ended up in France. And amazing story. So anyway, and plus, like I said, her kids also got a Nobel Prize. So very smart family. She was, by the way, a chemist. I just thought I'd throw that in. Chemical formulas. What they do is they tell us the type and the number of protons present in the molecule. Okay. They don't necessarily tell us the order. And this is something about, we talked about these numbers, how they come together, whole numbers. Now, we're going to put a subscript to represent how many atoms are for that element in that compound. If there isn't a number, we leave it blank. Okay. So for example, H2O, we got 2 hydrogen atoms and 1 oxygen atom. Okay. Now, you'll always be told, I'll always let you know who the central atom is because we need to make sure that it's bonded correctly. Because we will eventually get to the point where we're going to be drawing structures and so forth. So H2O, the formula is bonded formula, wouldn't be this. Okay. It'll be incorrect. It's because one didn't know that oxygen is the central atom. Plus, we're going to learn that hydrogen can't have more than 1 bond. And if you look at that central hydrogen, it's got 2 bonds. Now, with respect to electrons and this position in the periodic table and the model that we have, it just couldn't exist in that manner. It couldn't exist with any stability. So, for example, C3H6O3. All right. Granted, we don't know what that is right now. It could be multiple things. All right, it could be multiple things, and you will get problems like this. But please don't look them up, because C3H6O3 could be anything. There's a variety of combinations that you can make a compound. If you look it up, it's going to tell you, oh, it's probably acetic acid. Well, okay, could be, but it could be something else. All right. So don't dwell on what it is. Just dwell on the fact that there are 3 carbons, 6 hydrogens, and 3 oxygens in that molecule. Okay. If we look at this scenario, again, we don't know what that is, but here's something for you to kind of pick up now, because we're going to be using this quite a bit. If we go back to the periodic table, you're going to hate this periodic table after a while. If you go to the far left, we have what's called common, what are polyatomic ions. And look at the top one right here, NH4. That is a polyatomic ion. Those guys in that table, in this table here, we keep as a unit. We don't separate. That is how they're put together. If we need to add more than one of these guys, we put a parentheses around it and then a subscript. Okay. So we never separate them. Those are what they are. We got nitrates, nitrites, sulfates, sulfites, etc. Hydroxide, cyanide, acetate. We're going to learn more about this. Okay. But the thing to take away at this point is that when we need more than one, we put a parentheses, and this is why you see this written like this. NH4, it's a polyatomic ion. And we need a parentheses there because we need 2 of them. And there's be a reason why we need 2 of them. We're going to learn how we put these together. Okay. So we need 2 of those units, and then to the right of the 2, the subscript 2, we have a carbon, and then that's bonded to 3 oxygens. So what does that tell us? That tells us that within the parentheses, we have 2 hydrogens, 2 nitrogens, 8 hydrogens, okay, 1 carbon outside of parentheses, and 3 oxygens, for a total of 14 atoms. Now, why are we going through this exercise? Because eventually we're going to need this information. Because notice something on the periodic table, every one of these elements have an atomic weight. And so we're going to go back. Once we identify how many of each we have, we're going to multiply that by the number of those elements times the atomic weight to figure out the total atomic weight or the molar mass of that particle. For example, oxygen. Oxygen is its formula, water, H2O. Water has 2 hydrogens, 1 oxygen. If we look at the atomic weights for each of those elements, we got 2 hydrogens. Each one is 1.01 gram per mole from the periodic table. So it has 2.02 grams per mole. We'll talk about the units later on. The oxygen has 16. So the atomic weight for water is 18 grams per mole. Okay. So this is why we're going through this exercise, to be able to identify how many of each atoms we have. So here again, this is called ammonium carbonate. The name right now is not too important, but it will later on, because you're going to be able to look at that formula and determine its name, ammonium carbonate. Anyway, 2 nitrogens, 8 hydrogens, 1 carbon, and 3 oxygens. There's a total, for a total of 14 atoms in that particular formula. Okay, how about this one here? We got H3PO4. I know you don't know what that is, but I'm sure you had ingested some of this material at one point in your life. Okay. FYI, is just simply phosphoric acid. If you drink a lot of soda pop like me, you drink a lot of this stuff. Okay. So you got 3 hydrogens, 1 phosphorus, and 4 oxygens. Okay. If you get a lot of upset stomach and you drink a lot of Tums, this is probably what you're ingesting. Calcium hydroxide. And notice that parentheses. That should tell you, I got a unit here. One of these units that I was talking about. Here it is right there, OH. We call that the hydroxide. Okay. So it's, if I need more than one, I put a parentheses around it and then a subscript. Here, I need 2 of them. So I put a parentheses around it. And guess what? Ca is calcium. The OH is hydroxide. The name, calcium hydroxide. Yeah. All right. So we find that in Tums. And then the last one, aluminum. And then we got another parentheses here. So SO4, sulfate. All right. So for the first one, we have 3 hydrogens, 1 phosphorus, 4 oxygens. We have a total of 8 atoms. Second one, we have 1 calcium, and we have 2 oxygens, because remember, we got the parentheses there that telling us we got 2 of those what are called hydroxides, and 2 hydrogens, total of 5 atoms. And then the last one, which is by the name, is aluminum sulfate. How do I know aluminum sulfate? Well, I recognize that I got a parentheses here, which SO4, and I go, that looks familiar. I go back to my table here. Guess what? SO4. Okay. And look at its name, sulfate. Okay. So from that, I can deduce the name and say, I know that Al is aluminum, SO4 is sulfate, hence its name is aluminum sulfate. So there's 2 aluminum because of the subscript. In the parentheses, there's 3 sulfate units. That means I got 3 sulfurs and 12 oxygens for a total of 17 atoms. Okay. And where are we at? We're almost done with it after. All right, so that's how we count the number of atoms. Eventually, we're going to use this counting technique to actually figure out what we call the molar mass, because now that we know how many of each atoms we have, we know how much the total atomic weight for each atom that brings into the formula. So we will add up the atomic weight for calcium, for example, for calcium hydroxide, 2 oxygens and 2 hydrogens, and that gives us total atomic weight, otherwise known as molar mass, which is information we're going to need down the road. The law of definite composition. That means that, as we talked earlier, stated that there are 2 hydrogens and 1 oxygen for the molecule of water, H2O. Well, we won't demonstrate this here, but if we go through some real simple calculations, which we will when we get to that point, it's determined that for H2O, it has 11.2% hydrogen and 88.8% oxygen. Okay. And regardless of where the water comes from, if it comes from here in Arizona or the other side of the world or outer space, H2O is H2O, and that is the composition, 11.2% hydrogen and 88.8% oxygen. Okay. And we use that technique as far as finding the percentage, because as a synthetic organic chemist, I would send samples out to figure out the percentage of each component, and then that aids us to come up with a structure. So, with that being said, guess what, guys? We're done with chapter 4. Now, the first 2 weeks, the first 2 weeks are kind of hectic, a lot of stuff thrown at you, but I think from this point forward, we'll probably get about 1 to 2 chapters a week. You know, it's fairly small. In fact, some chapters, one chapter is only like 10, 12 slides. That's like way down the road. So anyway, My weekend is full. I got a lot of grading, especially some homework needing to do, some of the homework, to grade some of the homework, plus the exam. I need to do manually grade some of the questions. So if you don't see your number there yet, you should see it by Sunday, Monday at the latest. Bear with me. I got 23 here, 24 in another class, and 24 in the third class. So my plate is a little full. Anyway, any